All right, welcome. I am Ryan Holger with Temperature Equipment Corporation. As you likely know, this is a repeat of a topic we did for the Peoples and North Shore Gas Trade Ally event a couple weeks ago. There were a little bit of technical difficulties with that broadcast service, so they asked us to repeat it today, and maybe even another day. We'll see. I may do it twice here, so we can make sure everybody that wants to see this topic can see this topic. And I'm also going to record it as well, so everybody should have a chance, right? All right, so this originally started out when we planned it months ago as an ERV topic because that fits in nicely with the utility rebate program. However, things kind of evolved, obviously, the past several months. So it kind of evolved into a COVID topic as related to ERVs. So that's kind of how we ended up with this topic here. So this is what we're going to try to address today in our brief hour. I'm going to talk 1,000 miles an hour to get it all in. We're going to determine if filters can catch the SARS-CoV-2 virus. We're determining if UV lights can kill the virus, if humidity control will help, if fresh air and ERVs will help, and then we'll throw in a few tidbits about some other stuff we might be able to do to help manage this virus. A good half of our time will be spent on the ERV side of the equation since that's the original topic, but we're going to address all these other things as well. So first up is filters. I'm assuming everybody knows what a filter is and the basics of how it works. What you might not know is what your filter can actually catch. So hang on one second. What is this that's popping up? It needs to go away. Okay. Everybody can still hear me, right? I'm assuming yes, because nobody said no. All right. So you got to figure out what your filter can actually catch. So in order to do that, you got to figure out how big the stuff is. How big are the items that I'm trying to deal with? So if I get my little laser pointer out, up on this bar across the top, we have microns. This is micrometers. We just call it microns. This tells you how big stuff is. So the smaller the number, the smaller it is. So something like your hair is over here in the 20, 30, 40, 50, 60 range for the width of your hair. Whereas the things we're talking about today, like bacteria, is much smaller. Viruses, very small. Gases, even smaller than viruses. So if I'm hoping to catch some of these really small things, I'm going to have to do something different than the normal in terms of particle control. My viruses, 0.001 microns to like 0.04 microns or so. To give you a little bit of a visual on what that really kind of looks like, this big giant circle is pollen, like the pollen in the air from plants that your kids are allergic to, right? Bacteria, significantly smaller. Virus, even smaller still. One more way to look at that, over here on the right is a size 10 particulate matter, which is a typical measurement of a particulate that we're looking to reduce in outside air coming into buildings. That's pretty big, visually speaking. Red blood cell, which I envision as in my head as being pretty small, barely seeable, barely visible. 2.5 particle matter, which is the other measurement we look at a lot. 2.5 and 10 are the ones we measure a lot. Bacteria is smaller than that. And then COVID is not this big picture here. It's that little tiny dot where my red mouse is. We just blew it up so you can kind of see it. It's super small, way smaller than bacteria and particulate matter. So we're dealing with tiny stuff. However, if I put it on this same chart, it's actually as big as any other virus, if not slightly bigger than most other viruses that we deal with in the HVAC world. All right, so here's my normal range of viruses, and I'm plotting the SARS COVID-2 virus on here, COVID-19, and it's like almost 0.1, right? So it's pretty big for a virus, but it's still super small compared to bacteria, mold spores, pollen, sand, hair, and that kind of stuff. So how does your filter work? There's 4 main mechanisms that your filter will use to catch stuff. In this example, stuff is going to be dust. This blue circle is a piece of fiber inside my filter. It could be a piece of plastic, it could be fiberglass, something like that. And then I have airflow from left to right. And then coming in my airflow, I have this little dust particle here. So if that dust particle comes in and makes a head-on collision with the fiber of my filter, on one of the fibers, direct hit, we call that impingement. And that sort of makes sense. That's easy to kind of conceptualize in your head. Crash into the brick wall, and now he's just sitting there, right? Interception is I didn't crash into the brick wall. I kind of had a glancing blow, right? So I'm on the interstate getting on, and I didn't drive off the ramp, but I kind of grinded myself along the guide rail, and eventually I came to a stop, right? So this case, he grinds himself along this fiber. The friction between these two guys causes him to adhere to the fiber, and we call that interception. Straining is the super easy one to think about. This is basically your spaghetti strainer. You pour the pot of spaghetti in there. The water is small, so it fits through the gaps. The spaghetti is big. It does not fit through the gaps. The same thing with these particles here. My dust in this case is bigger than my air particles, so the air makes its way through the gap, but the dust does not. It gets stuck between the two pieces of the fiber. Now, as you might imagine, if this piece of dust gets stuck here, that means any dust coming behind him is going to get stuck behind him, even if it's a little bit smaller. The dirtier your filter gets, the better your filter gets at capturing stuff. Right? It's kind of weird, right? We always tell you change your filters, change your filters. The dirtier your filter gets, the better it is at being a filter. However, it's also good at stopping airflow at that point, and that causes all kinds of other problems in our buildings. So we got to change the filters to keep the airflow up, but as far as catching stuff, the dirtier the better, until it breaks or until it clogs up too much airflow. The last one, diffusion, is a little bit harder to explain. And I always kind of debate whether I should even have this slide in here or not, but if I don't, it makes it much harder to explain a few of the things we're going to talk about later on. So in order to understand diffusion, you first have to understand that really small stuff, smaller than my dust, so something like a virus or smaller, doesn't really care too much about airflow. And it doesn't really care too much about gravity. It really doesn't deal with those things at all. You probably understand that gravity is the attraction, is your body falling to the earth, right, pulling you down. But really, your body's also pulling up on the earth. The earth's pulling you down, and you're pulling the earth up. However, your mass is like almost nothing compared to the mass of the earth. So the earth doesn't move towards you. You move towards the earth, right? But all the things in the universe have this attraction to each other. Gravity is what we call it when it's the people being pulled to the earth, or the rock being pulled to the earth, or the tree being pulled to the earth. But when you're really, 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 really small, like a virus, you don't have like any mass at all for the most part, barely anything. So the earth doesn't pull very hard on you. So it's not like viruses in the air like settle down on the countertops or the ground. They kind of just float around the air doing whatever they want. And also because they're so small, they don't get stuck in the airflow very well. Air coming across them, it doesn't push on them like a sail and move them along. They're so tiny, most of the airflow just goes around them. So they don't really pay attention too much to gravity, and they don't pay much attention to airflow. Right? But what does happen is they're very small, like other very small particulates, and they bounce around a lot. They bounce off of other small particulates. So he collides into somebody here, bounces back, collides into somebody here, bounces back, and they're bouncing all over the place. And sometimes he'll end up accidentally getting into the airstream, accidentally getting back to this fiber, and then once he collides into the fiber, he's so close to them, their force nature, their van der Waals force, or their gravity between the two of them, if you want to say it that way, is pulling them together and clinging him on there. It's a little bit different some of the other mechanisms we use with the filters. Filters are tested with Ashrae standard 52. This is the what we call the Merv rating standard. 52.2 specifically. There's an old 52.1. You don't want to get involved in that. That's been obsoleted for 20 plus years. It was replaced by the new Ashrae standard. By new, I mean 20 years old. And that's where the Merv rating system comes from. So the Merv rating is going to tell us how well a specific filter that's tested can catch certain size particles. So here's my particle sizes down this column here. I got everything from really, really tiny stuff to 1 micron, 3 microns, and stuff that's bigger than 10 microns, and what Merv rating they'd get. So if you're only able to catch 10 micron particles, you basically have no Merv rating. I mean, you're Merv 2, 3, 4, which is useless, absolutely useless. Like the crappiest filter you could probably even get is a Merv 6, all right? I guess you could probably find one that's crappier. I'm sure you can. But the crappiest one that you would ever even want to put in a building historically prior to COVID would be a Merv 6. If my little buddy, my little COVID buddy, is up in the high 0.8, 0.9, almost 1 micron range, now I need to be down over here to have a shot at catching him. I'm not going to catch a COVID virus, or any virus for that matter, with a Merv 10 or Merv 12 filter. That's not going to happen. If you look at the Ashrae recommendations, Ashrae is recommending that at an absolute minimum related to this COVID pandemic, that you use Merv 13 filters in all of your air handling systems. And if you can, put a Merv 14 in, because that's probably going to catch the COVID. Merv 13, kind of dicey on whether it's going to get it or not. So Merv 14 is the recommendation from Ashrae. Merv 13 is the bare minimum from Ashrae if you want to start reopening your businesses and things like that. Can you use a Merv 15 or 18 or 20? Yeah, sure, you can use those things. Now, generally speaking, for the most part, as you move up higher in Merv rating, you're also going to probably have more pressure drop. So if you want to put HEPA filters in, that's awesome. It'll catch a virus if it gets back to the filter, but it's going to be a pretty decent airflow penalty to put a HEPA filter in. So 14 is kind of a sweet spot. Merv 15 maybe even if you can do that. So there's our particle, right? So I said it's just probably a little bit smaller than 0.1. So that kind of is putting us like, well, Merv 12 isn't going to get it done. I got to jump up to a Merv 13. By the way, if you're kind of wondering about the gap on this chart between the 0.3 and the 1, it's going to be a percentage. They only test certain size particles, and it's going to be a percentage of those particles, and they don't test, exactly 0.8 size particles. All right, we have our first quiz question. Now, for you guys that need PDH hours for your PE, assuming you registered and said you need those, you do need to answer these quiz questions in order to get those hours, right? So everyone's welcome to answer it. That's no problem at all. But you have to answer them correctly. There's 5 of them, and you need to get 3 of them right in order to get your PDH hours. They are not hard as long as you reasonably paid attention. So the first question I'm going to pop up, what is the current Ashrae filtration test standard? Your choices are 52.1 dust spot efficiency, Ashrae 52.2 Merv rating, and Ashrae 62.1 indoor air quality. Which is the one that's specific to filtration? While you guys are answering that for the next few seconds, I'm going to pop up the question box and see if people can hear me. Everyone can hear me, and no one has written any questions in yet. If you have any questions as we go, feel free to type them in, and I'll try to answer them as we go. And if not, I will answer them afterwards. One way or the other, I'll get them answered. So 71% of you responded. So if you need credits for PDH, respond right now, because I'm going to shut this poll in 3 seconds. 3, 2, 1. Awesome. And awesome. 91% of you guys got the correct answer. It is 52.2, which is the Merv rating standard. That may be the highest accuracy question I've ever got people get. So maybe that question was too easy. I'll make them all harder after this. All right, so, oops, hang on. Why is that beeping? No, I have to hide that to go back to the regular slide deck. That's why. All right, so we're back on the regular slide deck. Hopefully that was helpful to you guys. All right, so can filters catch COVID? Yes, they can if you put in a filter that's decent enough. Decent enough meaning you better go for Merv 14 or higher. And if you can't handle the airflow of that, at least put a Merv 13 in. Anything less than that, you shouldn't even be talking to your customer about the ability to possibly catch any of the COVID virus. All right, what about UV lights? What do those do for us? UV lights are definitely not new. We've had this technology for 50, 60, probably 70 years at this point. It's been around forever. We can do a whole hour subject on just UV light. But the UV light, when it shines on single cell organisms, it breaks down their DNA and it basically kills them. Right? It's if you walk outside on a sunny day, the sunlight is going to be killing your skin cells, breaking that down. Now you have a lot of skin cells, so you got some to lose. But if you're a single cell organism and you only have one cell, you really can't afford to lose that guy, right? Because that's all you got. So it'll kill viruses, bacteria, mold, all kinds of stuff like that. So it's not that clean of an answer though, right? It's going to kill a virus, and it definitely will kill COVID, but it's not that clean of an answer. So the bandwidth of light that we're using is 254 nanometers. Like I said, we've been using this for 70 years. The key thing to keep in mind is that I need a certain amount of intensity of light to kill something. Properly, that's called the CT value. Most of us just call it the kill dose because that sounds way more fun. Now, I know some of you guys probably know that you can't really kill a virus because a virus is technically not alive to begin with. Right? It needs a host to survive, whereas bacteria and mold can survive on their own. Viruses cannot. However, I'm going to say kill the virus anyway because I am not a biologist and I don't care. And saying I kill it is more fun than saying I inactivate it. So, but in order to kill it, I need a certain dosage, a certain CT value, and that's a function of the UV intensity of the light source and the time of exposure. And there's an actual measurement for that, microwatt seconds per square meter. This big long units a measure over here. Right? So UV energy and time duration is what's going to get my kill dosage. My energy is a function of how close I am to the light and how bright the light is to begin with. So just like with the sunshine, if you're on the top of a mountain, you're going to get more sunlight shining on you than if you're in a valley, right? You're closer to the sun. You will burn slightly faster. The same thing's going to happen with a UV bulb. UV bulb has a certain intensity, just like the sun has a certain intensity, and the farther I get away from it, the less intense it is. If I assume at 1 inch I have maximum power, when I get 2 inches away, I've lost 75% of the power. When I get 8 inches away, I've lost 92% of the power. So being close to the light is going to be pretty key in order for this to kill anything. And of course, if a virus collides right into the light bulb itself, he's dead. It's like a bug zapper, right? But if he doesn't collide into it, then I'm going to need a lot of time to get him. So how am I going to get this quantified, right? We mentioned there's this microwatt seconds per square meter unit of measure. And there are tables readily available for how much of that UV dose you need to kill all sorts of things, bacteria, viruses, mold, etc. There's tons of them that are documented. This particular table shows you 2 columns, 90% reduction and 99% reduction. 90% reduction means 10% of these dudes survive. 99% means 1% survives. And of course, you can go to 99.9, a third column, meaning only 0.1 even survive, right? So this is the intensity that you would need for those type of kill rates, right? And the same thing over here for viruses and mold and so forth. If I take one of those examples, right, and I don't remember which one I took when I made it, Bacillus subtitle, whatever that word is, to get 90% kill rate, I need 11,600. The bulb that I have selected to use, which is a pretty good bulb, it puts out 800 microwatts per centimeter squared at 1 foot distance. That's what he can put out. So if I do some basic math over here, at 1 foot distance, he puts that out. Okay, great. So my normal airflow at 500 feet per minute on a HVAC coil, and at 8 feet per second, that's 500 feet per minute. So 8 feet per second. Every second, the germ that's in the air, he's going to move 8 feet down the duct or down the airflow path, right? In order for me to get the exposure rate that I need 14.5 seconds. I need the 11,600 divided by the 600. I need 14 and a half seconds of shine time on this kind of bacteria to kill 90% of it. Well, at 500 feet per minute, I'm only going to get 8.25 seconds within the 1 foot distance. So I'm not going to get enough to kill it all. Am I going to kill a little bit of it? Sure, because some of it's going to be closer than 1 foot. Some of the germs are going to come by only an inch away from the bulb instead of a foot, and the intensity will be higher. But all the germs that are 1 foot away, I need 8 seconds. Now the duct's pretty big. I may be 3 feet away from the bulb, right? Now I need like 50 seconds or something ridiculous like that. I was already starting to jump onto the influenza one. Sorry, that was the bacteria one, 14 and a half seconds. Influenza, to kill 99% of the flu, I need 8.25 seconds. That's the one I was describing here. So to get that kind of exposure to kill influenza in the duct, I'm going to have lights every 2 feet. So I got that 1 foot distance on each side for 66 feet of length. If you don't want to put that many in, okay, then you're going to have to slow down the air a lot, down to like 50 feet per minute instead of 500, which you're not going to be able to do for HVAC purposes. So will the UV light kill influenza and bacteria? Sure, but it's not going to kill much of it because I don't have enough light bulb shine time. If you want to look at COVID specifically, which I'm sure all of you do, it wasn't in this other chart because this chart was a little bit older. We've had this in the slide deck forever. But I did find this. Now, this is not an official thing published by any entity. This is from one specific researcher's test data, but it's all I could get my hands on, so that's what we used. So here's the intensity usages for this. Here's my 90% kill rate. Here's my 99% kill rate. Here's my 99.9% kill rate. So COVID compared to influenza is actually pretty easy for UV to kill. So I can kill 99.9% of it with only 2,700 microwatt seconds per square meter. All right, doesn't sound that bad. Let's do the math on that guy. Assuming I got the 500 feet per minute by my coil, which is 8 feet per second, I need 3.5 seconds of light shine exposure at a 1 foot distance to inactivate the COVID-19. So I would need 28 feet worth of light bulbs spread apart 2 feet from each other, right? That's like 14 bulbs I need. That's not realistic. So if you're expecting to put UV lights in your HVAC coil and have that kill COVID for your occupants, it's not going to happen. It'll kill a little bit of it, right? So when we say UV lights kill COVID, it's not a lie. It's just it's not going to kill very much. And that's assuming the virus even gets entrained into the airflow and makes its way back to the UV light. It might not, based on our previous discussion with the filter. Viruses don't really give a crap about airflow. So if you get it back to the UV light at all, then you need a lot of intensity, which you can't get on a regular system to kill this guy. So what the hell is a UV light good for? It's good for keeping coils clean. That's all it's good for. Putting UV light in your return duct is stupid. Putting it in your supply duct is stupid. Stupid's a technical term. UV lights need to be shining on the coil because the coil doesn't move. So I have all the shine time that I need is available to me. So it keeps fixed surfaces clean like evaporator coils and condensate pans. It's really good for that. It is not good for cleaning air. We've been saying that for at least 15 years that I've been doing training over here. Don't put UV lights in to clean the air. Put UV lights in to clean the coil. Now, there are air cleaners that happen to have a UV bulb in them that do clean the air, right? For some of you guys are familiar with some of those, like PCO technology or Respicare's Oxy 4, those kind of things. They coincidentally have a bulb in them, but they are not UV lights using UV light to kill germs. They are using UV lights to activate a catalyst to generate oxides to kill germs. It's a different discussion than a regular UV light. There's also a benefit, since this is a energy topic we did for Peoples and North Shore Gas, there's actually an electrical benefit to keeping the coil clean. It will improve airflow because the dirt won't be there blocking it, and it'll also improve heat transfer between the refrigerant and the air, or between the water and the air if it's a hydronic coil. So I will get some improvement in efficiency by keeping my coil clean. So not only is it less gross and has less things growing on it, but I can also save a couple bucks. All right, quiz question number 2. All right. Which are HVAC mounted UVC lights the most effective at cleaning? I guess this is going to be another easy one because I just said that 1 second ago. Supply air, room air, coil surfaces, or room surfaces? I guess I should have waited and asked the questions a little further down the road. That's okay. Like I said, the questions aren't there to be hard. They're there to make sure that you are alive and well and paying attention. Then I can give you PDHs. I'm looking at your guys' quiz questions, and I don't see you guys typing anything at the moment, so I'll just wait on that. It's like 79% of you guys voted. So I'm going to close the poll in 3 seconds. So if you need something, pick something. And we're done. And that was actually a higher percentage correct than even the last question. So you guys definitely paid attention. So it's really good at cleaning the coil surface. Will it kill stuff in the supply air? Sure, but minimally. Return air? Sure, but minimally. Room air? Sure, but minimally. Room surfaces? Yeah, UV light's actually really good at killing germs on room surfaces, but not HVAC UV lights. I can mount UV lights in the space and have that purify surfaces. The issue with that, other than needing a lot of UV lights to do that, is I can't have the UV lights be on when the occupants are there, right? So it's got to be some kind of like nighttime cleaning mechanism. But it wouldn't be mounted in the ductwork. It'd be mounted on the ceiling or walls. All right, back to the slide deck. I don't see any questions from you guys. Type them in if you got them. So can UV lights kill COVID? Yes, they can, but not with the UV lights that you guys are using on HVAC systems. So kind of more of like a no to that answer. Can humidity control help us minimize COVID? So you probably have seen this chart. It's been around forever. And by forever, I mean 1985. This is directly in the Ashrae handbook. It's called the Sterling chart. I assume somewhere there's a footnote that says someone named Sterling made it, right? But in any case, it comes off of study data from that 1985 Ashrae research project, showing that there's lots of things, bacteria, viruses, mold, etc., that don't survive well when it's drier in the summer, like don't have really high humidity. Let's say it differently. If it's really low humidity or really high humidity, certain things thrive. Certain viruses thrive when it's dry or when it's humid, but not in the middle. Same thing with bacteria. Fungus, as you guys already know, mold essentially, thrives when it's moist, right? You know, door shocks, electric shocks happen more when it's dry, all those kind of things. If I can keep stuff between 30 and 60%, life is usually pretty good. This one shows 30 to 60. That's the original Sterling chart. You might see newer ones that show 40 to 60. That's a pretty common range that you'll see, especially if you listen to any of the humidifier manufacturers and stuff like that. They'll have charts that show 40 to 60%. And I used to be a 30 to 60% guy, and this summer I am now more of a 40 to 60% guy. And this is why right here. So I'm going to show you two different other slides off of studies. Now, this is not from COVID data. This is from a surrogate coronavirus, so a different coronavirus, which, by the way, when you look at anybody who's claiming they're killing COVID these days, they're probably testing it on a surrogate because they probably couldn't get their hands on the actual virus. So in any case, it's all we have to go with right now. So we're going to make the assumption that all coronaviruses have some similar behaviors. So this is showing you here how many viruses survive up the vertical axis versus the horizontal axis, how many days of survival that they had in those kind of environments. And then the blue, black, and green lines are showing you different humidities. So the black line with only 20% humidity, viruses survive a pretty good long time, which is probably one of the reasons, and I'm assuming this is probably true for other viruses like influenza. That's why flu season tends to not be in the middle of July when it's humid. It tends to be in the drier times because the virus survives longer, hence it can infect more people. However, when things get really humid, I have the same kind of issue. The green line is a really humid scenario, 80%. I get a pretty long survival rate then. Not as bad as the dry days, but still pretty long. And then blue, the best case scenario is 50% relative humidity, and things are going to pretty well die off. Let's say here, this 90% of them die off in 2 or 3 days, right? Somewhere in this range over here, or actually 3 days, right? I've killed 90% of these guys off. So it's a much faster ability to naturally get rid of stuff. I don't really want to wait 2-3 days to get rid of a virus, right, in my building or whatever, but I'd rather have the humidity be in check to help this whole discussion along and get rid of some of these guys that way. This is a similar chart from that same study. Once again, viability up here. So this is 90% virus survival rate, 99, 99.9% survival rate right here. And in this case, I have humidity on the vertical axis, 20, 40, 50% relative humidity, 80% relative humidity. And the lines are various temperatures. Now, unfortunately, this is all in Celsius because this was a European study, which is kind of the way things go sometimes when you're trying to get data early on. So I've overlaid Fahrenheit on here because I just couldn't handle looking at the Celsius anymore. It was baffling me. So this black line is 40 degrees. That's pretty cold, so that doesn't really matter in my life. The red line is 105 degrees, which is pretty hot, so that doesn't really matter in my life. This blue line works out nicely at 68 degrees, which is kind of a common temperature for wintertime in a lot of commercial buildings. And even if you keep it at 70, then you can just in your mind envision this line to be slightly lower than the blue line on here. But as you can see, when I get kind of to that 40 to 60% range, it has the best effect on the viruses. So if I have a normal indoor temperature like this, and I can keep your humidity between that 40 and 60% range, 50% being the sweet spot target, I can inactivate a lot of viruses just by a matter of them sitting in that temperature and humidity environment. So quiz question number 3. All right. True or false? Maintaining indoor space humidity between 55 and 75% minimizes bacteria, viruses, and mold. And let me pull up the questions from you guys and see if we got anything. Looks like we do have a couple of things on here. Tim asks if I have a presentation on bipolar ionization. I will briefly talk about bipolar ionization at the end of the presentation today. It's kind of an add-on discussion. We also have a lot of IAQ-related webinars that are re-recorded on our site that incorporate lots of stuff, including bipolar ionization. I don't have one that's just bipolar, but there's ones that include bipolar, oxidizers, filtration, all kinds of stuff clumped into one like 2-hour training module. So it's factored into there. Julia asks if we can share the slide deck. Yes, I could do that. Then she says their counter. I'm assuming counter to some of the information we're receiving from other reps. Yeah, so there's always a problem with getting information from reps, which is why I don't do any sales. My company does. I don't, because I don't want to focus on that. I like to focus on data and facts. But yeah, I can send you that stuff, and I can pull the sources of where it came from. I'm gonna forget, Julia. Honestly, I will. So if you could send me an email to remind me, because I can't take any notes right now. So Ryan.Hoger, Hoger, at tecmungo.com, and I will be sure to get you that tonight. Julia says, with UVC, couldn't you space the lights closer to each other to obtain the energy intensity required to kill the virus? You can put them closer together, but still, even at that 1 foot distance. So if you put them all at 6 inches apart, if you just put lights everywhere, 6 inches away from each other, you're still going to need 4, 5, 6, 7 seconds for some of those things I was quoting before. Instead of 14 seconds to kill that bacteria, I might need more. I might need less time, but it's still not going to be enough time. And plus, I don't know who the hell wants to buy 47 light bulbs and put them in an air handler and space them 6 inches apart. That would be a lot of light bulbs to constantly change when there's a lot of other technologies, like Tim mentioned, bipolar ionization, that I could probably get things done with instead. But yeah, I guess you could put more of them in to get more intensity. Just like if we had 2 suns shining on the earth, we'd get sunburned a little bit more, I guess. Of course, I don't want that. All right, I'm closing this poll question. So 82% of you got the correct answer, which is false. 50 to 75% is not a good relative humidity range to reduce those guys. 40 to 60 would have been the good range. And I definitely don't want to be above 60. If you follow Ashrae standards, Ashrae standard 55 for human thermal comfort will specify that you need to keep things below 60% RH. And Ashrae standard 62.1, which is indoor air quality, will specify an absolute maximum of 65% relative humidity to avoid mold growth. So I definitely want to keep things under 60. With that being said, the new Ashrae standard switched from a relative humidity recommendation to a dew point recommendation. So I'm just saying it based on the old one before somebody corrects me, which I'm sure one of you will. All right, back to these slides. So can humidity help minimize SARS? Yes. So that's a yes for filters. If you put in Merv, probably 14-ish. That's a no for UV lights. Yeah, technically they do, but no, they're not going to kill it in a regular usage and installation application. Humidity will help minimize it. Yes, not a lot, but it'll help a little bit. Next question is, what about fresh air and hence ERVs? Can they help us dilute the virus down? I'm assuming you all have seen this project. I say it with that tone of my voice because it's become a pain. There was some restaurants in China that early on in the whole COVID thing back in February, March timeframe, where somebody went to a restaurant sick with COVID and got other patrons sick as well. And immediately everyone blamed the air conditioning system, right? So we're going to try to figure out, for one, if the air conditioning system even does spread COVID, right? And this popped up in all kinds, hundreds of publications carried this story with the same information and the same lack of detail, by the way. So the good folks at Ashrae have researched this. This one comes from an Ashrae Madison chapter, but Ashrae National and other chapters as well have all taken a look at this exact restaurant application, this exact one in China. And this is kind of the information that was found. First off, they had they had 4 ductless mini splits in there. So as you guys know, ductless mini splits are not known for their fresh air ability. You can combine them with dedicated outside air units, and then you can get some really good fresh air. But just on their own, they don't really have any fresh air coming into them. So in this case, somebody was sick in this back row of tables. I think the people in red are the ones that eventually got sick, and the people in yellow are the ones that did not. So nobody in the front got sick at all. But somebody in red sat down here, was sick, coughed, sneezed, whatever. And then did the AC system spread it? Yeah, just because it has air movement, not because it's air conditioning, just because it has air movement. Right? It moved the airflow from one side to the other side and then back around in the return. So people that were in this area were significantly more likely to get exposed than people in these other areas were. Now, the biggest thing that they didn't mention in any of those like regular news stories, but that the Ashrae folks point out, is that the ventilation rate in that exact restaurant was 1 liter per second. I don't know what the hell 1 liter per second is, so just do the quick math. That's 2 CFM of outside air. 2 CFM. Nowhere in the United States is our code anywhere near that. The least amount of fresh air required in a building anywhere in the United States is Wisconsin, and they require 7.5 CFM per person. This is 2.5 CFM. It's like nothing, right? 0 per person, essentially, right? For a normal restaurant, you would, if you're following Chicago, Chicago's the most airflow outside air required in the state or in the country. Wisconsin is the least, and everywhere else in the country pretty much follows Ashrae 62 or IMC or some derivation of those. And you're probably going to need 10 CFM. Well, a restaurant probably needs 7.5 CFM per person, and I think it's 0.06 CFM per square foot, and you add them together, right? Either case, 2 is extremely low. So they basically have no ventilation air. That's the real crux of the problem, not just the fact that they have an air conditioner. So people need ventilation. You can't just lock a building down, seal it up, have the pollutants be in there, and then never bring any fresh air in. I mean, I guess you could, but it would not be advisable. We need the fresh air, not because we necessarily need the air from outside. We need to get rid of the air from the inside. So by bringing new air in from outside, somehow it's going to shove air out somewhere else. I don't care if it's going out a crack, out the front door, out an exhaust system, but if air's coming in, air is definitely leaving. Because if it didn't, the building would blow up like in a balloon and it would explode, right? So if air's coming in, air is definitely going out, and I want air to go out. And that's how I'm going to get the germs out, is one way, is to bring new fresh air in that hopefully has less germs and push the inside germs out. Now, you have to understand, too, that indoor air is way worse than outside air. There's bad things in the outside air. Sometimes there's high particulate counts, there's high humidity, there can be pollen in the air, stuff like that. But indoor air is way worse than that. So fresh air is generally perceived and by code explained to be much cleaner than indoor air is. Now, if you live next to some kind of like oil refinery, maybe that's not true. But for most places, that's going to be true. So I need to get that fresh air in to get the bad air out. We want to distinguish between combustion air and fresh air. Commercially, I think most of you guys get that. Residentially, it gets confused a lot. Like, well, I don't understand why I need to have a fresh air intake. I got this this two-pipe system for my boiler, bringing the combustion air in that way. Dude, that has nothing to do with this. Combustion air is separate from ventilation air. So I need air coming into the building for combustion appliances, fuel-burning appliances that have exhaust, like whatever they take out, I got to make it back up. And then I also need to have fresh air for the occupants themselves. In addition to that, some places I'm going to be more inclined to exhaust from. So those kind of places, bathrooms, kitchens and stuff like that, I'm going to focus on exhausting air out, which is going to draw fresh air in. So move things at their pollutant source. Other spaces like an office or school, I don't have a dedicated pollutant source like I do with a stove, right? So in that case, I'm going to bring fresh air in and let it pressurize the building positively and spread the fresh air that way. Ventilation rates have changed a lot over time. This is a table. This one's specifically to office buildings, and it's based on the Ashrae standard. For brevity purposes, right now we're around 17.5 CFM per person. I say around because it's additive. Since 2004 for Ashrae and 2006 for IMC. You take the per person. For an office, that's 5 CFM per person, and this per square footage. And for an office, it's 0.06 CFM per square foot. And you add them together to get your ventilation minimum requirement, minimum. And we say it's about 17.5 based on a typical office density. Can you do more than this? Yeah, you can do more than this. And some of the recommendations, including from Ashrae, as related to COVID, are to beef up your ventilation rate if your mechanical equipment can handle that, if you have the capacity to do so. So there's all kinds of tables you can look this up in. The Ashrae 62.1 standard and the International Mechanical Code have the exact same tables in this regard, so you can look it up in either place. And this is pretty much the code everywhere in the country, except, like I mentioned, the state of Wisconsin and the city of Chicago proper. Chicago suburbs, this is what we would follow. City of Chicago has their own tables, but it's a similar thing. You look it up in the table and you bring in the right amount of outside air. And this is just one page of the table. There's like 3 pages of tables on this thing. So how's the ERV fit into this discussion? So ERV stands for Energy Recovery Ventilator. That's what the acronym means. The first question I always ask when somebody's talking about an ERV is how much outside air do you need? If you don't need a lot of outside air, I'm not going down this path, right? If you got a lot, now I'm interested. The next question is how much exhaust air do you got? Because what's going to happen is I'm going to reclaim the energy from your exhaust air, and I'm going to transfer that energy, not the dirty air, but the energy to the outside air. If you don't have a lot of exhaust air, it's going to be hard for me to find the energy. And if you don't have a lot of outside air, financially, why am I buying this? Like, you only need 100 CFM? Not super interesting to me. Oh, you got 1,500? Oh, you got 10,000 CFM of outside air? Oh, okay. Now it's super interesting from a financial standpoint. One of the keys is in getting the exhaust air near the intake air. If my intake's over here, my exhaust on the other side of the building, that's going to be tough to do. Because I need to get his BTUs out of this guy and transfer them over to this guy. So I need the intake and the exhaust to be close to each other, preferably through the same piece of HVAC equipment if I can get it to happen. What's this all going to look like? So let's do a winter example first because it's easier to illustrate. So down in the bottom right, I got a 7-degree day, pulling cold, fresh air in from outside to meet ventilation code or just extra outside air, whatever it's going to be. I need fresh air. I bring it in 7 degrees, right? Somewhere else in that space, I have return air, or I have exhaust air, you'd probably call it, that I'm going to throw away. Maybe it's from the toilet exhausts, maybe from somewhere else, but it's 72-degree conditioned air. I'm going to throw it out, exhaust it away. Instead of exhausting it straight out the building, I run it through a heat exchanger, and that heat exchanger sends the BTUs over to the outside air, and that 7 degrees gets warmed up to 53 degrees in this example. And then the 53 goes into the rest of the hydronic heating coil, gas furnace, whatever you got. So I'm going to use the heat from the exhaust air to preheat the outside air. In the summertime, exact opposite thing happens. Now I got some 95-degree air getting sucked into my building for fresh air, and somewhere I have pre-cooled 75 exhaust I'm going to throw away. All right, well, now I take that warm air, or that warm energy from the 95 degrees, and I transfer it into the exhaust air, thereby raising the exhaust air from 75 to 89, and I throw it away. But in return, it cooled my outside air from 95 down to 81. So on a 95-degree day, I'm going to have 81-degree air being brought into my air handler to then be further mixed with the return air, cooled down with my cooling coil, etc. You'll also notice I'm also drying it out. I'm dropping it from 78 wet bulb to 68 wet bulb because some of this moisture also went into this side of the heat exchanger. So heat and moisture both go this way and get exhausted out, leaving me with cooler, not cool, but cooler and drier air. And in the wintertime, it was the opposite. The heat and humidity, heat and moisture from the exhaust air transfer their way into the outside air, thereby preheating me, and with the wet bulb from 6 to 40, pre-humidifying me. It's kind of sweet, right? So the benefits are energy savings, better humidity control, smaller HVAC equipment. I know that's weird because I work for an HVAC equipment supplier and I'm telling you to buy a smaller chiller, buy a smaller boiler, buy a smaller air handler, right? It's kind of weird. The payback period can be fairly quick. This is a cheat sheet chart. I did it. It's the first time I ever said it on the first try. Cheat sheet chart that we made years ago. I'll give you a couple examples off it. We don't have time for the whole thing. But if I take 1,500 CF of outside air, which is a pretty good amount, and I run it through a specific ERV that I selected here, it is going to mean that I need 4 tons less cooling than I was going to get. If I needed a 15-ton unit, I'm now in the market for an 11-ton unit, right? I'm going to need 120,000 BTUs less of heating. So I'm looking for a smaller hydronic coil or a smaller gas heating section. I'm going to get on in this example, it was a 95-degree day with, I believe, 74 wet bulb. Coming off the heat exchanger, I'm going to get 80 degrees and 67. 80, 67 is no coincidence. At our office, we specifically select ERVs targeting 80, 67. We could do ones that are worse, and we can do ones that are better, but the better ones cost more money, and the ones that do worse don't have a lot of benefit. So we kind of target 80, 67 as kind of a cheat because 80, 67 is the same inlet conditions that all your evaporator coils are rated at. So we figure if we can get to 80, 67 with the ERV, it's like your evaporator doesn't even have any outside air anyway. So it's kind of a nice spot. And this was based on a negative 10-degree day. So this guy's going to get 50 degrees coming off the heat exchanger on the outside air. It's going to heat it up 60 degrees. This payback was pretty good, 1.5 years. If you look up here, small stuff, 500 CFM, the paybacks start getting pretty bad, 4 or 5 years. If you look at a residential ERV, which is typically 100 to 200 CFM, the paybacks are typically double digits in years because you have a lot of technology, but you don't have a lot of airflow to recover energy from. So it's kind of hard. I'm not saying you shouldn't put an ERV in residentially. I'm just saying don't do it for the financial reasons. Do it because of altruistic reasons. You know, you want to be good kind of thing. One more example on here, 12,000 CFM of outside air, which is a lot, I know. That reduces my cooling system by 31 tons. So if I was looking for a 30, that wouldn't work. I was going to say a 30-ton rooftop. A 60-ton rooftop, now I'm in the market for a 30-ton rooftop, right? Almost 1 million BTUs less heat I need. And the payback is really good on this one, 0.1 years. That's like a month, right? I picked that one because it was the best payback. In this case, it's because it got us out of a semi-custom rooftop down into a small chassis rooftop, which is more commodity priced, if you will. You probably know if we get down to you get under 30 or under 25 tons from most manufacturers, they have 2 or 3 choices. One of them is a really cost-effective model kind of thing. So you can get out of that semi-custom big rooftop into a commodity, small, high-volume manufacturing, low-price rooftop. That's why the payback was so fast on that one. There's different kind of heat exchangers that we can have in the ERV. Wheels are pretty common, as are fixed plate cores. Heat pipes and run-around coils are not that common. There's numerous reasons for that, one of which is they don't comply with energy code. Not that they don't save energy, they certainly do. They don't comply with the energy code, though. There's also terms you might need to know, HRV versus ERV. HRV is heat recovery ventilator. ERV is enthalpy recovery ventilator or energy recovery ventilator, depending on who's saying it. HRVs only do sensible energy, so they only do temperature. They heat up or they cool down the outside air coming in. They do not affect its humidity in any way, no moisture transfer. An ERV does enthalpy, which is sensible plus latent, so it heats up and humidifies, or it cools down and dehumidifies. It does 4 functions instead of 2 functions. In the interest of time, I'm going to power through this a little bit and just let you know that the current codes for ERVs for energy code standpoint are Ashrae 90.1 and IECC. And they've had this mapping system since the 2012 IECC. I'm going to show you the map here in a second. In addition to the map, you also need to have 50% enthalpy recovery, meaning sensible plus latent. And because runaround coils and heat pipes don't do latent, you can't get 50% total because you can't get it all from the sensible side. So you kind of have to use wheels and plates. This is what the map looks like. We are climate zone 5A here in the Chicagoland area. Everything in green is climate zone 5, and everything to the right of this line here going over by Colorado is the moist climate, which is A. So we are 5A. For you guys up in Wisconsin, I saw some Wisconsin guys log in. If you're up in the Milwaukee, Madison areas, you are climate zone 6A. For the purpose of this discussion, you are the same as the Illinois people. I'm sure Wisconsin people love it when I say stuff like that. The current code, the 2015 and 2018 energy codes have 2 tables. There's the top table, which is for normal projects. And then there's the bottom table for projects that operate nearly 24/7, 8,000 hours a year. There's 87, 60 hours in the year. So they're operating like 6+ days a week at 24 hours a day kind of deal. So they're operating a lot. So if I look at climate zone 5A or 6A, that's this yellow bar across here. If I have 70% outside air, which is pretty large amount, and my fan is 1,000 CFM or larger, my supply fan is 1,000 CFM or larger, right? So that means I have 700 CFM of outside air, then I have to do an ERV. If I look over here at 30% outside air, if I have 30% outside air on a system that has a total of 5,500 supply air, got to have an ERV. And if I'm down here in the really small range with only 10 to 20% outside air, then I have to have a pretty large air handler to require an ERV. But if I go to systems that operate most of the time, right, most of the time meaning like hospitals, Walgreens, the BP gas station or something like that, right? They're never closed really. Those people are going to have to do ERVs pretty much every project unless they have less than 10% ventilation air. And some of them may, but most of them probably don't. So they're probably going to have to do an ERV for just about everything in those cases. Candidates for putting an ERV in, unless it's code required, obviously you got to do it. But if it's not code required, places you might want to do it are places that have a lot of people. Because places that have a lot of people have a lot of outside air requirement, and a lot of outside air and a lot of exhaust air are needed in order for an ERV to make sense. So movie theaters, gymnasiums, hospitals, these are the kind of places that have large amounts of outside air. So I want to have those places be the ones with the ERVs. Showed you this chart before, although this is a prettier version of the Stirling chart. So humidity control, yes, important. We explained all that. A normal system without an ERV, a normal DX system, I design it for a certain amount of people, for a certain condition outside, right? Some design day, if you will, right? In this example, it ended up being 15,000 CFM I needed. I selected a coil that got me 53-degree dew point, which is awesome, by the way. And I set my thermostat for 75 degrees, and that all ended up yielding me a 48% relative humidity set, value in the space, which is great. However, if I have a part load scenario, meaning everybody doesn't show up, or it's not as hot outside, and I still run my 15,000 CFM like almost all the existing systems out there and small offices do, or retail or whatever, I end up with an average dew point of around 65 because it's going to run, the stat's going to satisfy and shut off, and then it's going to run and shut off and run and shut off. So I'm going to have 50-degree dew point, then I'm going to have 72, then 50, then 72, and on average I might get 65. I'm not going to dehumidify a lot if I don't keep that air temperature down below the dew point. So my thermostat still says 75 because it always gets exactly what it wants, but that results in not very much runtime. So my relative humidity in the space ends up rising. This is not a surprise to anybody, hopefully. There's lots of things we can do. We can do humidizer, we can do fan speed control, all kinds of things we can do to reduce that. One of those things is going to be an ERV. If the humidity is high, partially because of the outside air requirement, an ERV is going to help. If I just have high humidity in the space for internal reasons, well, ERV doesn't do me a lot there. But if I have high humidity and the outside air is making it worse, now ERV starts making a lot of sense. Now, it can make sense on other applications too because of this reason right here. This is a psych chart. Hopefully, you've all seen this before Vertically, 20, 40, 60, 80, 90 degrees of dry bulb temperature. Horizontally is grains of moisture, so little droplets of moisture, if you will, 60, 80, 100 grains of moisture. A normal rooftop or air handler HVAC system is designed to do all of the work of the red bubble. Certain temperature day over here on the right, certain humidity on the top, certain low humidity on the bottom, certain low temperature on the left. However, when I have an ERV, it preheats it and or pre-cools it and or dehumidifies it and or humidifies it. And now my HVAC equipment selection is smaller piece of equipment, and it only has to do the work of the blue bubble now, because the ERV is trimming all the sides down to make this guy a little bit more appropriately sized for more moments of the day. So instead of having this part low condition be a problem, it actually works out pretty well if you have an ERV, because your part low condition doesn't seem much different than your regular condition from the compression standpoint. Runaround ERVs, like I said, these are not going to meet code because they only do sensible. So if you have to have an ERV for code compliance, this doesn't help you. But if you have a big building and you want to just do it, if you have exhaust on one side of the building and fresh air on the other side of the building, a long distance between them, that's when this would make sense. You drop a hydronic coil in the exhaust, a hydronic coil in the fresh air intake, and you put a circulating pump between them to move the BTUs from one to the other. Heat pipes is kind of similar, but instead of water in there, you have refrigerant. So now it's not going to work for long distances. It only works for small stuff, really close to two airstreams that are near each other. But I have refrigerant in these pipes. There's no compression in this discussion, just refrigerant in the pipes. And inside the pipes, I'm going to evaporate refrigerant on one side. It's going to migrate to the other and condense and have like a little mini refrigeration cycle in between them. But once again, it doesn't get low enough to hit the dew point of the air, so it doesn't do any latent work. It only does sensible, hence it doesn't comply with code. I'm saying that in my office, we can help you with runaround loops and heat pipes. Even though I'm saying not to do them, we do them. So I'm not just bad-mouthing them just because. I'm just saying they're not going to comply with code anymore. Fixed plates come in both sensible or latent versions. Sensible versions would not comply with code. Latent versions would. The easiest way to tell them apart is a sensible version is going to be metal only, like the bottom left one over here. A latent version is going to have some kind of membrane in it or what looks like paper or fibrous material. I would say paper, and the ERV guys yell at me. Fibrous material that can wick moisture through without the actual air molecules. Those guys work much like the wheel I showed you earlier. They crisscross the two airstreams though. So one airstream goes through this way, the other airstream goes through this way. Those airstreams don't touch. One guy warms up a metal plate, the other guy receives that heat. And then the airflow goes and warms the next plate up on that way. So I got like 5 channels, or actually more than that. I got 25 channels of airflow going one way and 25 channels of airflow going the other way. And they're each just warming up or receiving heat from a metal plate. And then if they're in enthalpy style, then there's also a fibrous material between them that wicks the moisture through with vapor pressure. And then we have an ERV wheel, which is very common also. This guy absorbs BTUs in one airstream and then rotates the wheel to the other airstream. So on the fixed plates, the airstreams crisscross. On a wheel, the airstreams go straight through. They don't crisscross, but the heat exchanger moves between the two of them, transferring BTUs from one to the other. Right? These things move pretty slow. It's like, I was going to say it's like a record player, but most of you probably aren't old enough to know what record players are or how fast they turned. But it's going to be 30, 40, 50 revolutions per minute. I don't want it to go too fast. I have to have time to absorb the heat, rotate, and then release the heat. So it is fairly slow rotation for these wheels. Wheels do way more work than anything else. And once again, we do wheels and we do cores and we do sensible only and we do latent. We do all of these at our office. So I'm not picking on anybody in particular. But wheels can do a lot more energy transfer for a given amount of cabinet size. More because the wheel's in motion, I get more BTUs that way. There are some reasons not to do the wheel. Some cases, the wheel might have a little bit of bypass around it, a little bit of accidental air leakage. Most applications, that's totally fine. But in some applications, you might not be allowed to do that. For example, if it's like an FDA regulated facility, right, and they don't want anything leaking from the exhaust air into the supplier, okay, you're not doing that. You're doing a fixed plate in that case, not a wheel. But if it's an office or a school, yeah, you're going to do a wheel. There's ways to couple this guy to the HVAC equipment. I could have the ERV be standalone. This one's ducted into the space. There are separate air handlers and fan coils that heat and cool the space. My fresh air goes to the ERV and I dump it into the space. That's fine. You can do that. This is common with ductless and VRF. The only problem with this is that dumping 50-degree air on someone or 80-some degree air on someone, which is what I'm going to get from the semi-conditioned effect of the wheel, it's not very good. So I'm going to want to do something different than that. One way would be to duct it into the fan coil. Instead of dumping it in separately, bring that guy in and dump him into the fan coil, mix him with the return, then heat and cool him further if needed, and distribute it to the space. That's probably a better way to do it. You can build an ERV into the air handler itself. So this is fairly common also. It's going to be a stacked air handler. In this case, I have a wheel in here that's rotating between the two, and one airflow is going through this way. The other airflow path is going through this way. And then ERV wheels rotating between the two of them, transferring the BTUs. We do have bypasses on this one, because when it's an economizer day, I want to open up the fresh air intake damper a lot more than normal to suck in lots of extra cool free air. Well, in that case, I don't want to recover my building heat and dump it into the incoming air because I literally want cold air. I'm asking for it. When I ask for an economizer, I want cold air. So I don't want to preheat it on accident. So I open up these bypass dampers and shut off this wheel in this case to let all the airflow skip the heat exchanger for those economizer days. So it looks like in the inside, right? So return air goes through, it gets filtered. You have to filter the air before it goes to the heat exchangers of the ERV because I don't want to have to clean those because that's pain, right? I want to clean them minimally. Filter, ERV, where it gives up or takes BTUs, sends the dirty air molecule out. Fresh air comes in, goes through the filter on this side. I got to filter both sides of the ERV. Picks up the BTUs that this guy dropped off, and it comes in and gets heated further if needed and moves its way into the system. There are some quirks that you might see too. In this case, I have two ERVs. It could be two wheels or it could be two cores like I'm showing here. It doesn't matter. It works the same way. One of them is treating outside air. One of them is a reheat wheel or reheat core in this case. So return air comes in, does this heat exchange with the outside air coming in, the dirty air molecule exhausts. I think we got that part. The fresh air came in, picked up whatever BTUs it needed. It comes through here, and then what it does is it drops off some BTUs in this heat exchanger, goes into the cooling coil and gets subcooled, wraps back around itself, and picks up the BTUs that it had left. So instead of subcooling and then reheating to temper it back up to a neutral temperature, which is no longer allowed by code, unless you get the reheat from a free source, here's your free source. This is one way to do it. You could also get hot gas reheat off a compressor. You could have solar panels on a roof, right? Solar thermal panels. But in this case, my air came in, dropped off some of its heat that it already had, got subcooled nice and low to wring a lot of moisture out of it, wrapped back around, and picked up some BTUs to temper it back up to 63 or 65 or 70 degrees or whatever they needed. If you have an existing air system, you could put the ERV, wheel-style ERV, in the duct. The ducts have to be close to each other, but you can get a cartridge that slides in between the two ducts if you want to do that. You can get ERVs that are pre-built into packaged systems, packaged rooftop systems. That's an option as well. You could take a regular rooftop and an ERV and duct them together. You could have an ERV here on the right and a rooftop on the left and then duct them together below the roof line. You could do that. You could get a curb that we call a combo curb that has this ducting physically inside the curb instead of you building it in the building. And I can have the air exchange happen that way between a standard rooftop and a ERV. And the reason we do that sometimes is because standard rooftops are pretty inexpensive. Not that we can't do it this way. You certainly can. And that's an option, and some applications need that. But other jobs where I only have, say, 50% outside air, this may be the way to go. It's kind of ugly. I got a rooftop and an ERV sitting on one giant ugly curb. But, hey, no one's looking at the curb on the roof, so who cares? And then there are small ERVs that you can bolt onto the side of an existing rooftop. We don't do that very often for the simple fact that most rooftops are already oversized. And when I put an ERV on, I need less cooling, so that makes that problem worse. Sometimes we do it when there's a change of usage of the space. Hey, this used to be an office building. Now it's going to be a fitness center. We need more tonnage and we need more fresh air. What can we do? Well, you can keep the existing rooftop possibly and add an ERV onto it to get the work done. So we do that sometimes. The big key, though, like I mentioned, is having the outside air and the exhaust air near each other. If anybody wants, let me know. We have a 1.5 hour webinar just on ERVs only that I can certainly send you guys a link to. It's free. It's pre-recorded. It's been on our site for a couple of years. I can send you that if you want to dive deeper into ERVs specifically. All right, let's do quiz question number 4. I'm going to a couple last things for you guys. All right, number 4, which is not an IAQ benefit of an ERV. Choices are fresh air for space dilution, lower energy cost, improved humidity control. Which one's not an IAQ related benefit? All right, let me see what else we got question wise. All right, so Sean's question, which is long, related to the UV kill rates. UV bulb manufacturers talk about multiple pass and the ability to kill viruses UV. They tend to show the same math you did, but add air changes per hour and discuss the fact that multiple passes are additive as well, etc., etc. All right, so that's true. If I have, let's just say I have a little pot of viruses. They make their way to the return air. They go past the UV light. They don't get a lot of exposure to light because they're going through at a really high velocity, but they get some. The logic is then they take another loop back around to the building and they go through again and again and again. And by the time they go through 4, 5, 6 times, they've been in enough shine time of the UV light that they get killed. Just like your skin cells in my example, walking out into the sunshine. If I run out to the car to get my wallet because I forgot it out there, I'm probably not going to get a sunburn. If I go out there and I work for an hour and a half, or I go out there and back in and out there and back in and out there and back in, out there and back in, yeah, I might get a burn. All right. Same kind of thing is going to happen here. Here's the only problem with that, and we sell a lot of UV bulbs. I'm not bashing UV bulbs. The only problem with that is that I'm relying on the fact that the virus is going to get back to the UV light again. I already told you the virus doesn't really give a crap about airflow to begin with. So the chance of him making it into the return duct to get to a filter is tough. And to have him do it 5, 6 times to go past the UV light multiple times, it's pretty dicey. So yes, it's true. They are not lying to you. The UV light, if it doesn't have enough exposure the first pass, after enough passes, it will eventually. It's just, do you think the virus is going to get there enough times? How many times does it have to move around? And how many times does it have to go past my face to get there? Right? So yeah, it'll help kill that stuff. I'd rather have something that's going to kill it much faster. So if you're going to put a UV bulb in, why not put a UV bulb in that also creates oxidizers and have the oxidizers attack the virus in the space instead of waiting for the virus to get back to the bulb? Have the bulb make me something that sends oxidizers in the space to kill the virus there. I'm going to come back to these other questions some of you guys had as well. Let me just get through the last few slides, and then I'll come back for anybody that wants to hang on. All right, I'm closing this poll question. 60% of you got it correct. Saving energy is not an IAQ benefit. This one was a trick question. I gave you really soft balls for the first couple. This one was a little trickier. All 3 of these things are benefits of an ERV, but only 2 of them are an indoor air quality benefit. Saving energy doesn't help my air quality. I was mean on that one, but he had the softballs early on. So, all right. So what else can we do? There are things I mentioned a couple times. I mentioned PCO. I mentioned bipolar ionization. Actually, somebody asked about bipolar ionization. These are technologies that can be installed in a duct system that, in the case of PCO and bipolar ionization, that they will create something, ionizers, oxidizers, something that will be distributed into the space, and then that something will actually attack bacteria and viruses. That's what I want to happen. I want that to be my control mechanism. I don't want to wait for the bad thing to make its way to the air handler and maybe get caught or maybe get killed. Why don't I just go out and kill it myself, right? That's kind of my thought process. I've had some of these technologies in my own house this is going on in the 9th or 10th year I've had this technology in my house. Different versions of it from different manufacturers. And we do it in our own office buildings. We do it in our classrooms for a long time prior to COVID. Nothing new there. The bipolar ionization not only can help neutralize some of these germs, but it also charges particles coming in, which makes them clump larger together, right? If I got a positive thing and a negative thing, they'll stick together. And now after a couple of them stick together, they're bigger. And now all of a sudden there's a chance that the airflow brings them back to the filter. And because they're bigger, they might get stuck in the filter. It's generally accepted that bipolar ionizers improve the Merv rating of a filter. Now, you don't get a new Merv rating because they don't have a separate filter test for both, right? But if just in your head, like, oh, it used to be a Merv 12, I put this bipolar ionizer and it's like a Merv 13 or 14 because it's making everything bigger. Active particle control, something Secure does, it has the same kind of benefit as bipolar ionization. It's a really good Merv 15 filter, but it also charges particles, positive and negative, clumps them together, which means they're bigger and big enough to get stuck in the airstream, and they can make their way back to the filtering system. So these are all things you want to study a little bit further on. I apologize for not having time to, really go through them all today. Maybe I will because my slides just locked up. Oh, okay. All right, my last slide. It's kind of what I was just saying verbally. So here's some Merv ratings for filters, Merv 8, 10, 13, 15, and so on. And here's pretty much the estimated chance of that filter being able to catch a virus of the Sars type. Now, once again, this wasn't COVID specifically. It's a Sars surrogate because that's what people can get their hands on in their test labs. But let's just pretend that it is COVID for now because I have nothing else to give you for information. So this is the percentage that those things would catch. So if I put a Merv 13 in, which is what Ashrae says is the bare minimum to have a chance at catching COVID, it might catch about 46% of that. If I were to combine that with some UV lights, it would beef up my kill rate, right? Now, that's just something I put enough UV bulbs in to do enough work. If I combine the filter with an ionizing system instead of a UV light, so like a bipolar ionizer or that secure thing that I was just talking about, right? That changes a little bit more, and now my Merv 13 gets me up to almost a 99% kill rate. Right? And if I have, even better stuff, I got a HEPA, which is already awesome. It makes it awesomer, I guess. I don't know how you want to look at that. If your system can't handle a Merv 13, okay, I get it, right? You don't have the ability in your current system to handle that level of static pressure drop. Then you decide Merv 10 is the best you can do. Merv 10 sucks compared to Merv 13. But if I combine it with an ionizer, 89, 90% killer rate, it's not that bad. It's relatively speaking, it's pretty good compared to 12%. So if you can't get it done with just a filter, you may have to combine it with another technology. Maybe it's UV, maybe it's ionization, maybe it's secure air, maybe it's PCO. You might want to combine it with one of these other things that I had mentioned a minute ago. All right, last quiz question. This one is super easy. Everyone gets it right. Oh, dude, man, my bad. Okay, I see what's going on here. Okay, sorry. You guys probably were yelling at me on the questions and I didn't see it. This was the stuff I was mentioning with PCO and bipolar ionization. That wasn't very visual, so that was easy. This is what I was saying with the improvement in filtration rate. So I apologize. I left it on the question screen. I forgot to switch it back to the slide deck. It's my bad. What I was saying was if you take a Merv 10 or Merv 13, right, a Merv 13, Ashrae's bare minimum for a chance at catching COVID, catches 46% of this guy, of this surrogate SARS virus. If I combine it with ionization, it gets almost 99%, which is significantly better, obviously. And if I can't put Merv 13 in because of the pressure drop, and I decide Merv 10 is all my pressure drop in my current duct system can handle, I can put a Merv 10 in. By himself, he's almost useless, 12%. But with ionization, he's up to 89% capture or kill rate, however you want to look at it. That's what I was kind of illustrating in the last one. So I apologize for not showing the slide as I was saying that. It's my bad. The quiz question, everyone's going to get it right because it is not a question that's right or wrong. It's just a question for your feedback. So let me know how you heard about this particular webinar today. If you answer anything, it counts as being a right answer for your PDH credits to prove that you were here till the end. If you don't answer it, then obviously you get it wrong, but you don't know that I just said that because you had already left. All right, I'm like 7 minutes over my time, but I'm going to go through and answer any of the questions that are still on here for anybody that was still asking questions. So feel free to join me and stay if you like. We left off with Sean's question. Pete asks, ERV replace wheel or replace unit if wheel failing? I'm going to be honest. We've been doing ERVs for wheel ERVs for well over 15 years here. And I don't think we've ever bought a replacement wheel ever. Like the wheel, I would 100% promise you, is going to outlast the cabinet that the wheel's in. The wheel is a polymer. It's plastic. So it's going to go in a landfill and be there for like hundreds of years. Whereas the cabinet is metal, it's going to rust out. The ERV wheel will outlast the ERV cabinet that you have it in, for sure. Now, I take it back. We did order one of the pies. I can't do a pie shape. One of the pies off of, this is so bad, I'm an idiot. One of the pie pieces of a wheel before because somebody accidentally slipped and shoved their hand and screwdriver all the way through it. So if it's damaged like that, okay, fine. But generally speaking, not an issue. Most of the larger wheels, when you get above like 4 or 5 feet in diameter, they come in pie sections to make them easier to take out and clean. Pete asked if they sell replacement wheels only. Yes, they do. Air Exchange is a good source for that. Nizaria lost audio. Larry, good explanation. Screen froze on the quiz. Yeah, that was my fault. Quiz question, yes. Quiz question, yes. Okay, I think that was a lot of these questions in the middle. Okay. Okay, Alex asks, is there a risk of COVID jumping airstreams via the ERV wheel? Yes, not just COVID, but anything. So an ERV wheel has numerous different ratings associated with it. There's exhaust air transfer ratio. Well, first of all, there's just efficiency of the wheel. How many BTUs can it transfer, right, as a percentage. Then there's an exhaust air transfer ratio and an outdoor air correction factor. The short version of both of those is the outdoor air correction factor is how much outside air coming into the wheel accidentally leaks up the face of the wheel and goes back out the exhaust. You know what? Let me do it visually. So let me close this poll question. Let me, oops. Let me go back. Just pick any picture of any wheel will do it. That'll do it. That'll do it. All right, so this wheel on here, if I use him as my example, it's blocking myself. So any air that leaks up this face of the wheel and it accidentally goes back into the exhaust air is called the outdoor air correction factor. And you have to upsize the fan here to account for that. So if you need 5,000 CFM, but there's going to be 50 CFM that's going to leak up the front and go out, I need to get a fan that's 5,050 CFM. So that way I can get 5,000 actually going into the space because I'm going to lose 50 that way. There is also some air that could leak down this face of the wheel on the return air that's going to leave. That's called exhaust air transfer ratio. And that guy, he's going to leak air down the face of this. And I want to minimize this guy on the left because I don't want to buy a bigger fan, right, and pay energy to run it. I want to minimize this leakage on the right because whatever's in this return air may not be pleasant. So I don't want it to come back through. Now, the International Mechanical Code, depending on the class of air you're talking about, there's different classes for, offices, bathrooms, manufacturing, blah, blah, blah. Depending on the class of air you're talking about, you're either allowed to leak 5 or 10% of the air this way. So, for example, bathroom air, if I can leak 10% of my bathroom air, that means 90% of my poop smell leaves and 10% of my poop smell rejoins my supplier. That's allowed by code. That shouldn't be your goal. Obviously, you want to get close to 0. But you are allowed to have either 5 or 10% leakage on that end of the equation. Most ERVs are well below 1%. In fact, I don't think I've ever selected a wheel I think the highest I ever selected was 0.4%, not 4%, but 0.4%. It's a pretty small amount, and you will not smell the bathroom air with 0.4% leakage. So as far as being concerned about if there's COVID in the air and we get it back into the return air, if all that happens and a little bit leaks back around, that could happen. But if I didn't have an ERV, okay, what am I doing instead? I should have more return air. It's going directly into the space, right? I shouldn't say that way, but if I don't have 100% outside air and I have return air from my system that goes back into my evaporator coil, what about that air, right? So it doesn't matter if the ERV is leaking a couple tenths of a percent. If the main duct system is allowing 70% of the return air to go back into the supplier anyway, right? So your discussion would only have any concern and merit if we were doing 100% outside air and I had caustic air here. Now, if you're in the city of Chicago, you will not be using ERV wheels on that toilet exhaust example I had. They're allowed for regular air, like exhausting room air, in Chicago proper, but not for toilet exhaust. So then the discussion goes away even a little bit further. Don asks, what type of preventative maintenance does an ERV require? So we got a wheel on here at the moment for the picture. So for a wheel example, what you're going to do is there's going to be filters. You know what? I'm not going to go back to a drawing. Let's just pretend that it's on here. So I'm going to have a filter right here. Actually, what I'm going to do for you guys is when I close the webinar, it's going to automatically play a 5-minute video that shows you all of the guts inside the ERV. I'm going to point out what everything does. So feel free to stay tuned and watch that video if you got 5 more minutes to spare. But there's going to be a filter here on the ventilation air and a filter on the return air leaving, which seems weird. I'm filtering the exhaust air out. Yeah, because I don't want it to get any dirt to get on the heat exchanger. Those filters have to be maintained and cleaned regularly, or maintained and changed regularly. And then if for some reason you do a bad job with your filtration on these guys, hopefully you don't do a bad job, but if you do, and dirt gets into the wheel over here, then I can clean the wheel. Now, wheels are easy to clean compared to cores. Wheels, you could take these pie pieces out and you can wash them in a sink if you want to. You can clean them with non-acidic coil cleaner. If you got a hose bib on the roof, you can take them out and hose them down. So you got a lot of options to clean an ERV wheel. A fixed core, not so much, because instead of being this deep, it's going to be that deep, and it's going to be small passageways, so it's going to be really hard to clean down in between them. So on a fixed core, changing filters, yes, again, you can vacuum the surface of it, but after that, you don't have a lot of options. If you get dirt in there, it's pretty bad news. You'd probably have to use compressed air to maybe try to blow it out the best you could. But taking care of the filters on a core ERV is way more important than doing it on a wheel style ERV. All right, I am going to play that video for you guys, for those that are interested, if I can figure out where it's at. So I'm not going to play a video for you because I can't figure out where I pull it up from in the webinar tool. So I'm not going to do that, but when you leave the webinar right now, when you exit out, it's going to actually pop up the video for you and play it. And if for any reason it doesn't, I think it's supposed to, it said it would. Any reason it doesn't, let me know, and I will send you a link to watch it separately. But it should pop it up automatically for you. All right, with that, thank you guys for your time. If you answered the questions correctly and asked for PDH certificate, then you will receive that in the mail. It'll probably take about like 2 weeks or so to get her. She's going to type them all up. Kelly in my office types them all up, and she'll get them emailed out to you guys. All right, thank you for your time. I appreciate it.